In this section, we're going to talk about numeric conversions. When an expression has elements in it, operands, variables, literals, that have the same data types, the expression is evaluated using that data type as the result. When an expression has mixed data types, for example, a double and an integer, the compiler has to decide what the resultant data type of that expression will be. It can't be both because an expression has a single value and a single type. So there have to be rules to determine how to convert mixed data type expressions into a single data type as a result. Think of data types as a container. The title here is volumetric measurements. Think of them as like a gallon jug, quart, cup, etc. I believe that metaphor will help explain why expressions must be converted from one type to another when they're mixed. Let's assume, for example, we have two containers, a large one that holds a gallon and a smaller one that holds about a quarter of that, or a quart. These are metaphors for a double and an int. We're more familiar with volume here, so I believe it will make some sense. The problem is, let's say we're trying to add something, an amount of fluid held in a gallon container to the amount of fluid held in a quart container. Let's assume there's exactly 1 ounce in the gallon container and 1 ounce in the quart container. I can pour the volume that's in the gallon container into the quart container, and the quart container can hold it because I have a small value, 1 ounce. I pour that in, now the quart has 2 ounces in it. Everything's good. I don't spill any fluid. But that's not always true. Let's leave that 1 ounce in the quart, and then this time in the gallon, let's put 32 ounces, which is a quart. When I pour the 32 ounces into the quart container, a problem occurs. A quart can only hold 32 ounces total. So when I pour the 32 into the quart with the existing ounce, there's 1 ounce too many, and I spill it and get a puddle on the floor with an ounce in it. And that's the problem of moving data from a larger data type to a smaller data type. In fact, it's such a problem the compiler says you can't do that. It'll issue an error message. Now, it doesn't mean it cannot be done, but you, the programmer, have to explicitly state you want to do it, and the compiler absolves itself of any responsibility for spillage. Let's go the other direction. Let's say the gallon has 32 ounces in it, and the quart has the 1 ounce. But this time, we're going to pour the quart into the gallon. Well, a gallon holds 128 ounces. So 32 ounces plus 1 more ounce, 33 ounces, is not a problem for the gallon container. In the compiler's case, the compiler will always allow us to take a smaller data type, like an int, and add it or multiply it to a double and have the result be the double. A smaller data type is converted implicitly, silently, by the compiler to a larger data type. And I have examples in the slides later, but let me do one right now. If I'm going to assign a variable x to 3.0, which is a double, plus 1, which is an integer. The decimal portion, the 0.0 on the 3, implicitly is double. Unless we otherwise specify, the compiler will always convert a literal floating point value to a double, and the 1 will implicitly be converted to an int. Unless we specify otherwise, the compiler always takes an integer literal and puts it in an int. This is a mixed expression. We have a double and an int. So what the compiler does is convert the 1 from the smaller data type int to the larger data type double. So the problem really now becomes 3.0 plus 1.0. The overall driving motivation for the compiler is that it cannot mix data types because the bit patterns for an integer and the bit patterns for doubles are not the same. You can't just simply add them. One must be converted because the computer only holds small non-negative integers. Everything outside that is encoded and interpreted. Well, an integer is actually 4 bytes, which is an arbitrary size. It could have been 2, could have been 16. The Java developers decided it would be 4 bytes. So those 4 bytes have to be interpreted as a single number. So their bit patterns in each of those 4 bytes have to be treated as a unit. A double is 8 bytes, and it's not just a simple, straightforward pattern. A double has an interesting, twisted pattern of bits representing each part of it. I can't just add the integer to that. One has to be converted so that the bit patterns are interpreted exactly the same. That's why we must convert. The process of converting a smaller data type to a larger data type is called promotion. The sequence for integer types is byte, which is a 1 byte data type, to a short, which is a 2 byte data type, to an int, which is a 4 byte data type, to a long, which is an 8 byte data type. Each of these can easily be promoted to the next in sequence because an int will always be able to hold every value represented by a short. A short can always hold every value represented by a byte. In floating points, the float data type is promoted to a double. A double is twice as large as a float. It means it has a lot more precision and a lot more range. All integer types can be promoted to floating point types, which will be double. My example showed 3.0 plus 1. The 1 got converted to a 1.0, which is a double, and then the 2 were added. The bit patterns were now consistent. They could be added without complication. All of this promotion is handled by the compiler implicitly, silently. It does it for you because always the smaller type fits into the larger type with no spillage. We saw these examples. The bottom one, I have the 10L times 3. The L designates the 10 as long. The 3 is implicitly int. I have a long int mixed data type. The int has to be converted to a long because the long is bigger, and then the multiplication occurs. Now, I said the compiler issues an error message if we try to put a larger data type into a smaller container. For example, pouring a double a gallon size into an int, which is a quart size. It can be done. The compiler requires that the programmer explicitly cast the larger type to the smaller type. That means in the source code, there's going to be some evidence that the programmer intentionally did that conversion. The compiler is not responsible for the results because, as we saw, if the amount of data in the larger data type is larger than what the smaller data type can handle, there will be loss of data. When bits are chopped off, it's called truncation. Think of truncation as a large knife. It comes to the point of where the bits for the smaller data size line up to the larger data size, and it lops off the bits on the larger data size. An example, int x assign 3.0. 3.0 is implicitly double. We're trying to assign a double to an int. It won't work. Compiler says no. Let's try int x assign paren int paren 3.0. That will work because we're telling the compiler explicitly to chop off any unnecessary bits that don't conform to an int and shove it in there, and we get an x with a value of 3. I have a little note there. It says any value greater than 2.14 E9 is chopped off. That's the limit of an int on the positive. Of course, it also works on the negative. Anything greater than 2.14 billion will just get chopped off. Only the bottom portion will survive the casting from double to int. And notice you lose the largest portions of the data, not the smallest. You really do lose a lot. Here are more examples. The 3.0 E22, that's 3.0 times 10 to the 22nd power, cast to an integer, loses most of the data. The double value is well beyond the range of an int, and what results is integer dot max value, which is that 2.14 billion. In this third case, we'll actually have the value of 2.14 billion. And notice that doesn't correspond to 3.0 in any meaningful way. So what you get is something strange. Int x assign cast 3.14159. We lose data. We lose the decimal portion. It just lops it off. That knife comes to that decimal point and just chop, and all the 0.14159 is lost. The 3 gets converted and assigned to x. Now, in this case, the 3 corresponds to the 3 point whatever because it's within range of an integer. The previous example, the 3 times 10 to the 22nd power, wasn't close to being in range, but in the case of casting pi to an integer, the decimal value 3 is within range. Although not specifically in the book, I wanted to discuss 4 conversions from a double to an int. And these conversions need to be known and understood because different mathematical problems require different conversion. I will do some drawings that will help explain graphically. Let's start with the idea of casting a double to an int. And here's our double. Double has the decimal portion, and as we also saw, anything larger than the range of an integer just chopped off. So this is called truncation. It has a mathematical view to it. I'm going to draw a number line. We'll put 0 right in the middle, put towards negative infinity to the left, and we'll put towards positive infinity to the right. Obviously, none of our numbers will ever get large enough that we would consider them infinite, but the use of infinity just gives us a direction. I could say to the left. That's not mathematically precise. I will say towards negative infinity. Same with right. It's visually helpful, but it's not mathematically precise. So I'll say towards positive infinity or just infinity. What truncation does is it takes a number, and let's just put a few tick marks that represent integer boundaries. Doesn't matter which ones. And we'll put our double value with the decimal portion here. Now, what truncation does is called truncation towards 0. The way it works is that whatever that decimal portion is gets chopped off, leaving only the integer portion. That effectively pushes this double value to its integer value, which will line up right here. It goes in the direction of 0. So negative 3.14, chop off the 0.14, we get negative 3, which is larger than negative 3.14 because it's closer to positive infinity. Its movement is to a less negative number, which is moving towards 0. You'll see why I say 0 in a minute. Now, let's take the case of a positive number. Let's say it's plus 3.14. We lop off the 0.14. It goes from a more positive number, 3.1 something, to a less positive number, 3. After truncation, it would line up here. It moves towards negative infinity, that direction. But to summarize them both, notice the arrows point towards 0. Truncation towards 0 is the term. When we truncate, the number becomes closer to 0 than it was before. In the negative case, it moves towards positive infinity. In the positive case, it moves towards negative infinity. To unify them, we say it truncates towards 0. The second option is called the floor function. The math.floor method in the math package, what that does is the same number line. The floor function converts the floating point number to an integer that is always moving towards negative infinity. Let's take the same example. We'll take the dot here. And when we do the floor function, we're going to find the smallest integer that's as close to that as possible without being larger than it. The next smallest integer, which will line up right here. So if this is negative 3.14, the floor function moving towards negative infinity would make the resultant answer negative 4. It's the first integer smaller than the number, negative 3.14. The next smallest integer is 4. Remember, negative 3 is larger than negative 3.14. We would have to go to minus 4. Let's take the positive version, 3.14. Floor function moves towards negative infinity. It means it's going to move that direction. In this case, 3. 3 is the first integer smaller than the floating point number 3.14. It happens to be in this specific case, it just happens to be the same thing you get when you truncate. They're not the same operation. They just happen to have the same value for this number. Notice the arrows. For truncation, towards 0. They both point towards 0. For floor, they both point towards negative infinity. Let's do the same again, but something called the ceil function. Ceiling. If floor moves towards negative infinity, ceiling moves towards positive infinity. So negative 3.14 is going to move towards the next higher integer, which would be negative 3. So it moves this direction, and its resultant value would be negative 3. We still move towards positive infinity, which means the ceiling function for 3.14 will be 4, because it's the very next integer larger than that floating point number. And finally, one you're very familiar with is called round. Also in the math package, floor, ceiling, and round are in the math package. So we say capital M, ATH, period, floor, ceil, or round, in parentheses, and we put the number inside the parentheses. Rounding moves towards the value is closest to. Now I'm going to draw a second number line here. This will be 0. Just so I can have a larger amount of space. We'll say here's our point, minus 3.14. Well, if we round that, 3.14, the 0.14 is less than a half, so we're going to move in the direction of 3. The number we're minus 3.84. 84 is a lot closer to negative 4, so we would move to negative 4. We just move towards the closest integer. We divide the difference between integer to the left, that would be n minus 1, and the integer to the right, n. And wherever that number fits in here, the one that's closest is the one we round to. One exception. What if the difference is exactly in the middle? Most of us know the rule that if it's 0.5, move to the next higher integer. Well, that's just a rule. It's not required. There's no mathematical reason why it has to occur that way. That's just a generally accepted rule. Java doesn't agree with that. Java's default is even integer. Doesn't matter if it's negative or positive. The one that's even is the one it moves towards. There are actually many, many options for rounding. It can be changed. You can write a piece of code that tells it to do a different rule, like move to the higher integer. So that covers the 4 options: rounding, floor, ceiling, and truncation. One more comment about rounding. If you want to do your own rounding, all you have to do to a positive number is add 1/2 and then truncate. That will always give you the next higher integer. If, however, the number is negative, you don't want to add, you want to subtract 0.5 and then truncate. That will round. That follows the rule that we're most common with. Now, the 0.5 moves to the next higher one. The better way to say it is, this type of rounding moves you towards the absolute value that's higher. Negative 3.84 would move to negative 4 because the absolute value of 4 is higher than the absolute value of 3.